As we've discussed in our previous video, our reward function included angle, distance, and minimum LiDAR data. Distance was calculated by extracting our car body position and target position, which alters as we get close enough. Angle was calculated with the angle between the track vector and the car orientation vector. Track vector is calculated by subtracting next target position from current target position. Car orientation vector is calculated using getObjectOrientation function. We then found the dot product of these two vectors. Minimum LiDAR data literally extracted the smallest value of the LiDAR data. This was used in input to notify the car that it has confronted an obstacle. If the car crashes with the obstacle, we gave -10 as the result. Overall, angle and distance function to define its position relative to the target. The LiDAR data to note the obstacle position. Reward was calculated by previous distance minus current distance times 3 minus minimum LiDAR data. Unfortunately, this input and reward system did not work quite well. The extreme curved section was too difficult for our car to go through. There are two reasons why our car failed to follow the path. First, the target change was too abrupt for our model, and this immediate change was not suitable since our car tends to get to target linearly. Secondly, minimum LiDAR data was too limited. Situations like this can occur, and this issue is critical to avoid obstacles. Therefore, we changed our input model for our second competition. Our new input included angle divided by 360, LiDAR data 1 divided by 20, and so on. First difference is that we excluded the distance data. As we have walls presented, providing distance will only increase the degree and complexity of input. This issue can be sometimes critical, so we took it away. Furthermore, not only the minimum LiDAR data, but also the whole LiDAR data was used to provide sufficient information to the car. This application enables the car to fully map the situation for easier drive. Finally, we have linearized our input model to get rid of unpleasant unfairness of the given input. The range was set between 0 and 1. The overall reward system was maintained. Our training scene is shown. The path was given to the model. We have randomized obstacle positions, and this provided model more situations to learn. In addition, we trained the model in other scenes for the car to drive in any other lanes. However, our final tournament was not pleasant. The car just was not able to detour the obstacle, positioned right in the middle. We thought about two possible reasons. First of all, due to lack of time, our number of steps was insufficient to avoid other moving cars. Secondly, for similar reason, the situation with obstacles right in the middle was not trained enough. Our prediction is that lack of steps led to inefficient and wrong behavior. Therefore, we added more obstacles and situations by increasing episode numbers. The result was promising as shown. This has been Team 5's final presentation. Thank you for listening.